moment, psychologists in Britain and America are going right back to the beginning. It all starts with counting. One number word for each item.
No.
The number words have to be in the right order. One also has to remember where one started counting.
We need to find out how many Cookie Monsters there are.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Whoops, should we start again? Because we don't want to count anyone more than once. Let's start here.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11.
11? It's pretty hard, isn't it? Okay.
1, 2, 3, 4, 5. There are 6.
No,
What do you mean, no?
there are 5.
One also learns that the last number word gives a total number for the group. The puppet plays an argumentative devil's advocate. The children are tested to try and separate the different components of maths acquisition.
I'll tell you what I want you to do.
Psychologist Rochelle Gelman in California is trying to get Nina to disconnect the number labels from the objects.
Count, but make the baby be the number 1. Can you count all of them and make the baby be the number 1?
I'll try. 1.
No, start with the baby.
1.
It's harder than it looks.
2, 3.
And Nina deals successfully with her first abstract proposition. But doing the same thing with a larger number of objects was obviously going to be a tougher assignment.
Play again for me, but could you make the motorcycle here be number 5?
I'll try to.
Okay, we're waiting. Go ahead. It's going to be number 5 for the motorcycle.
Okay. Which one should I start off first?
Wherever you want.
1, 2. Which one is the motorcycle gonna be?
5. We're going to make the motorcycle 5.
Oh, I can't really do it.
But she will be able to later. She just hasn't had the experience yet.
Well, most people think that counting is simply reciting a list of words. But to count, you need to follow some principles. You may not be explicitly following them, but you certainly have to be following them implicitly. First is the 1-1 principle, which is that there be as many tags or words as there are items that you're going to count. The second is that list of tags must be in a repeatable order, so you can use the same list trial after trial. The third is the cardinal principle, which says that the last tag in your count list represents the cardinal value of the set. Additionally, it doesn't matter what the color is, what the shape is, what objects there are. You can use this procedure for any collection of objects, real or even imaginary. And then finally, no matter what order you count things in, as long as you use the 1-1 stable and cardinal principle, you'll get the same number. Now, that's an awful lot.
So just by learning to count, children assimilate a number of complicated rules and principles. And the young child can happily grasp the concept of infinity.
Is 1 trillion the biggest number there is?
No,
Why not?
because counting goes on forever.
How do you know counting goes on forever?
Because it always goes. If you count forever, then it goes up. Then you can never stop.
Put 1 checker in each glass, right?
Beyond counting lies the treacherous world of adding and subtracting. This is Professor Herbert Ginsberg at Harvard University talking to Josh.
Okay, now you can't see the checkers in there, can you? Inside the glass? Right. Can you tell me, do both glasses have the same number of checkers, or does one glass have more checkers than the other?
They have the same amount.
They both have the same amount. Okay, watch what I do now. I'm going to take a black checker. I'm going to put this black checker in here. And then I'm going to put...
The red one has more.
The red one has more. How come the red one has more?
Because you put 2 in the red one and 1 in the black one.
Oh, but I did put something in the black one, didn't I? Doesn't that have more?
No, the red one has
The red one has more.
Even without being able to see the counters, Josh is perfectly confident about concepts of more and less. But watch what happens when he can see the counters.
Okay? Now take a look at those 2 lines. Do I have more checkers, or do you have more checkers, or do we both have the same?
We both have the same.
Both have the same. Okay. Now watch this. I'm going to take your line of checkers, and I am going to spread them out like that. Okay? Now take a good look again. Do we both have the same number of checkers, or do you have more, or do I have more?
I have more.
You have more checkers now. How come you have more?
You put mine out.
I spread yours out. Okay.
The visual image has a stronger impact on the mind than the abstract concept of number.
Well, I'd just like to ask you some questions. What does 1 and 2 make?
Maths in the abstract is very hard. British psychologist Martin Hughes is talking to Ross, who has a year or 2 yet before he goes to school.
All right. What does 3 take away 1 make? Don't know that. What does 2 take away 1 make? Not know that one. Has anyone ever asked you questions like that before? No. Okay. I think they're rather hard questions, aren't they? Let's do something else. Shall we play a game with this box like we did last time? Do you remember? What do you think's in there?
Red.
Bricks. Okay. All right. Now then, should we play that game that we played before? I'll show you how we played. First of all, put that brick in there, okay? Shut the box. Shake it around. You can hear it in there? Okay, now then, watch what I do. I'm going to put 2 more in there. How many's in there now, do you think?
3.
3. Can we have a look and see? You're right? You're right, aren't you? Look, there's 3.
1, 2, 3.
Very good. Okay, let's shut the box. 3 in there, and I'm going to take 1 out. How many do you think's left in there now?
2.
Are you right?
1, 2.
Right.
Now back to the abstract questions.
Now then, what does 1 and 2 make? How many is that?
3.
3.
Abstract and concrete begin to connect,
What does 3 take away 1 make?
but not always.
How many is that?
4.
3 take away 1.
4.
4. All right.
There are harder problems to come in simple addition.
3 plus 8.
3 plus 8 would be...
There are several ways you can add 2 numbers. Very young children have to start from the beginning each time and count all the way from 1 to 11. They quickly realize they can start from the 3 and then count on. Later, without being taught, they discover they can turn the numbers round, and if they start with the bigger one, far less effort is involved. Emily, talking here to psychologist Loren Resnick at Pittsburgh University, goes straight to the bigger number.
9,
Say it louder so I can
8,
hear.
9, 10, 11. Would be
Okay.
11.
Okay. How much is...
Research is showing that children invent their own, sometimes surprising ways of adding. Noah is adding 5 and 3.
You can use your fingers.
8.
Yeah, show me how you figured it out.
See, 5 takes 1 more away from 4, so it has to be 8.
Wait a minute, I don't understand.
No, you see. Now, 4 one more and you take one away from this 4.
Oh, so where'd you get the 4s, though?
You see, because you see, I got the 4s from the other way you can make 8.
I see. Like 4 and 4 make 8. And so that's how you figured out 5 plus 3?
Yeah.
Wow, that's pretty smart.
So very young children are more sophisticated at maths than we might think.
How many are we going to make?
The everyday environment provides opportunities for all children to form mathematical concepts for themselves in their own way.
12.
12. Can you make this into 12?
Yeah.
Okay. There we go.
Ah, must be heavy then.
Can you try and make them all the same size, or else some people will get jealous if they get smaller ones? Do you think that's right?
Yeah.
Okay.
See?
Bit big, I thought. Do you think we're halfway yet?
Now I've got 1, 2. 7.
Right. Do you think we've got enough to finish?
No. Yes.
Let's see.
5 more.
Oh, are they? Right.
I need that. Because look, 1, 2, 3, 4, 5.
Well done.
Now there's 4 more to... Oh, I need a little bit more. 6 more. 4 more to do.
Tom is about to make a remarkable discovery all by himself.
6 and 6 make 12.
How did you know that?
Because I know that's 6 and I know that's 6.
Now for a little multiplication and division.
And how many are going to come for dinner?
6.
6, if we have here then. So how many can we have each, I wonder? Do you think there's enough for us?
Yeah, we can all have them. That's 12. That means we can have more.
How many
Right,
can we
I'm
have?
just going to put them in
Hey, how many can we have?
There's 6 people and 12 of these.
So how many can we have each? How many can I have, Tom?
You can have 1, 2, 3, 4. 1, and I can have 1, 2, 3, 4. And Hezzy can have 1, 2, 3, 4.
Oh, yes. And
Come
what
on.
are Dad and Brondy and Simon going to say?
They can have nothing.
Oh,